Aloha, good morning, everyone. How was the exam? Not too bad. I didn't grade it yet. I will work on that soon, maybe this weekend. Um, you want me to do partial credit or you just want the scores from the Scantrons? What's our thoughts? Scores from the Scantrons? Okay, that'll save me a lot of time. Thank you. Nobody speaks up. Just kidding. All right, so it'll probably be next week sometime. I'm not gonna be doing it today or tomorrow. So don't get your hopes up for Friday, but maybe by next week I should at least have worked on it. Okay. Um, everybody feel like you had enough time? My OChem class, I didn't have enough time. Weird. I gave both class the test beforehand and I just changed the numbers. If you don't have enough time, you don't know how to study the practice exam. So in lab last week, we worked on a worksheet, right? Some of us worked in class, some of us worked asynchronously. So this stuff is kind of review. Basically, you should be able to identify the acid and the base in the reactants. And then based on whichever one was the base, after it gains a proton, which is a definition of the base, it becomes a conjugate acid. So you can see in this picture that it is blue to blue, right? So the base, after gaining a proton, now it has a proton to donate if you were to look in the reverse direction. So that's why it becomes a conjugate acid. In this case, water is the thing that is donating the proton. So it loses a proton. That's what makes it an acid. Whatever's left over after the loss of the proton. So you subtract one hydrogen, one positive charge to make it negative. That gives us the conjugate base. We can think of hydroxides as bases. Okay. Let's see. Um, so usually we've always looked at arrows this way. When we started talking about equilibrium, we started talking about reactions going in the forward and reverse direction. When we talk about these, sometimes the notes will have this because, or it'll have just a double arrow like that because I have a hard time figuring out this. But basically, if I write something like this or like this, that just means it's a reaction that has a forward and reverse direction, right? We're going to learn that most reactions do. There are some reactions that are so product driven or reactant driven if you write it in the reverse way. So a reaction that has an arrow like this, what would you expect its K value to be? What's our thoughts? Jack? Super high, right? If a reaction has a super large value, that means that that reaction is going to be product driven and pretty much it's not going to be making much reactants. When reactants can go in both directions, that's when we use this double-sided arrow. Okay? Um, so once again, just to summarize, a base accepts a proton, and after it accepts that proton, it becomes a conjugate acid. An acid donates a proton, and after it donates it, it becomes a conjugate base. So those are the terminology I'm looking for your homework and things like that. Um, real quickly, if we look at this, can we clearly see what this is becoming? So if I'm writing this as A, B, C, and D, which two things are related? Which ones? A and C. So A becomes C. And then we can see that therefore B becomes D. So what happens to A to C? Did it give off or lose a H plus or did it gain an H plus? It gained the H plus. So this is the base. This is the conjugate acid. Sorry, the colors are wrong. And then we look at water and it becomes OH minus. It gave a proton. So that means that this is the acid and this is the conjugate base. So we're looking at what happens to that thing. It gains the proton. The water becomes OH minus and it loses a proton. Therefore, it's an acid and the OH minus is the conjugate base. Now, the relationship between this one, HNO3, is becoming NO3 minus. Is the HNO3 the acid or the base, Cade? It is the acid because it lost the H plus. It gave up an H plus. So therefore, it's the acid, and the thing that is left is the conjugate base. The water and the H3O plus, what's that relationship? I mean, if you figure out one, the other one is the other one. So you can double check to verify that the H2O is in fact accepting the proton, but that's how we do that. Okay? Real quick conceptual check. If you think that it is A, raise your left hand. If you think it's C, raise your right hand. And if you think it's B, put your both hands in the middle like this. 1, 2, 3, go. Let me see some votes. I like that some of us are praying and stuff like that. How come some of us are not picking anything? Come on, pick anything. What happened? We woke up late for our 11 o'clock class and we didn't have time to shower. There's no one by you. It don't matter. So what do we think? Which is not a, so this thing here, are they separated by an H plus? Yes or no? So they're a conjugate acid base pair. Put down your left hand if you only have your left arm up. This thing here has an N and then it adds an H plus. So is that a base pair? Yes. So what should we be doing? Middle, B. So those two things are separated by an O. So that is not a conjugate acid base pair. Okay, so the answer is B in this case. Not the H2SO4 are both acids and they're not conjugate acid base pairs. Any questions on this? So like I said, this was our review from the lab. Let's jump into some new stuff. Look at all these things I teach on an everyday basis. Crazy, huh? So let's talk about strength of acids. So have we learned about strong acids before? Yes, no, maybe so. What do we think? Kayla, did you learn about strong acids last semester? Did you have Perry? Did he teach you the strong acids? Can anybody remember the strong acids from last semester? Or is that something that was not talked about? Anybody? All right, then I will teach you. Okay. So, strong acids. Anybody know what a strong acid is? So, like strength is relative, right? You could have a weak acid, but if it's 50 molar of that, it will burn the heck out of you. Okay. You could also have a strong acid, but if it's like 0.01 molar, you could probably drink it and not get harmed. You should never drink anything like that. But so acid strength is kind of relative. It kind of has to do with concentration, right? But the definition of a strong acid is on a strong electrolyte. Did you learn about electrolytes? Yes or no? Yes? What was an electrolyte, Ian? What was an electrolyte? You remember? I heard some people say yes. Bianca, what's an electrolyte? Huh? Anybody know it? Talk then. So an electrolyte is not, a salt is an electrolyte. Okay. And what do salts do when dissolved in water? What do they form? So is anybody, ions, very good. Okay. So an electrolyte is something that forms an ion in solution. Electrolyte solutions have the ability um, to conduct electricity. There's like a demo with a light bulb. You ever see that demo? Should we do a little video or should we just get talked about it? What do you think? Nah, forget the video. So basically, an electrolyte. Has you ever heard the word electrolyte before? Non-scientific term. Gatorade. So why do they pump up electrolytes for? What are they talking about? It's to replenish your electrolytes that you lose. Riley, how do you lose electrolytes? Not as a goalie. Just kidding. Well, when you run around, what happens when you run around? You sweat. Do you just sweat water? Sometimes if you sweat and you don't wipe it off, you can see like there's some like white on you, right? That's from salt that's left over. So when you exercise, you lose water through sweat, but that sweat also has potassium and sodium, maybe some chloride and things like that. Okay. So electrolytes are basically replenishing those ions in your body. Do you need to drink Gatorade to replenish your ions? Is that the only way you can replenish your ions is through Gatorade or some type of sports drink? What else can you do? I mean, water is not going to have any electrolytes in it. What, Merve? You can eat food, right? So food also has electrolytes. So Gatorade like tries to like market it and they make it sound like this is the way. Yes, it does sometimes replenish your electrolytes. In general, I think the amount of salt and stuff that you lose, the ions that you lose in your body, you can just drink water and let the food replenish it. But sometimes, if you go on like a 18-hour hike or something like that, at the end of that day, even when you drink water, you don't feel refreshed. Anybody in here ever go to Yosemite? Anybody ever climb Half Dome? So like I play sports, I do hikes, but one time when I went to Half Dome, full thing, one of my friends came with us at the last minute, didn't bring any water, so needless to say, we ran out of water early and we're drinking water. And honestly, like by the end, water didn't even feel like it was hydrating me. When I drank Gatorade, it felt like my body was like feeling better and stuff like that. I think because so much of those electrolytes were gone. You can make your own Gatorade. Okay. All you need to do is take water, add some salt to it. Does that taste good? Not really, right? So how do you make it taste better? Add some sugar. Sugar good for you? In moderation. It's not, huh? Coconut water has natural electrolytes, right? So that's why I know none of you never experienced things like this, but sometimes when people get these things called hangovers, you need something to help replenish some of those electrolytes also. So things like coconut water and things like that are also nice for getting that back in your body. So why is a strong acid a strong electrolyte? Based on this definition of an electrolyte that I've been saying, it's an electrolyte is something that makes ions in solution, okay? If you were to watch a video on electrolytes, what you do is you take different solutions, you take a light bulb that's plugged in, but electricity runs in a circuit. If you stick it in a solution that has positive and negative charges, you can get electrocuted, right? So that's one reason why you're not supposed to like use electronics in water and things like that. People back in the day used to say like, oh, this person died because they were listening to the radio in the bath and it fell in and it electrocuted them. Well, water does not conduct electricity, okay? How would you get electrocuted in a bathtub then? Any thoughts? It's not just pure water, right? If you're the water, so it's a cool demo. It's kind of not on this class, but you could look up a demo of this old guy like putting these things in. And the strong acids are strong electrolytes, meaning that they fully dissociate. Okay, so fully dissociate. So somebody shout out a acid for me. Hydrochloric acid is probably our most common acid that we're going to talk about. Does anyone know if hydrochloric acid is a strong or weak acid? It is a strong acid, okay? I'm going to give you a list of the strong acids that I want you to know. Strong acid means that we draw it with a one-sided arrow. When HCl is in water, it makes H plus and Cl minus, okay? A strong acid has fully dissociate or 100%. So if you start off with 1 molar HCl, you would have 1 molar H plus and 1 molar Cl minus. Everybody see that? You get 100% dissociation. Anybody know any other strong acids? Shout out an acid. I'll tell you if it's strong or weak. Hydrofluoric acid is actually a weak acid. So what do we think the different properties of hydrofluoric acid and hydrochloric acid is? Anybody ever watch Breaking Bad? Yes? No? Thought that's why you're in this class. What's the acid that they use to melt bodies in? Is it hydrofluoric acid? I only watched it once a long time ago. I feel like it was hydrofluoric acid, but hydrofluoric acid is a weak acid. Why would he use a weak acid to melt bodies? Because it's Hollywood. Could it be super strong? Could it be concentrated? Yes. So if a strong acid fully dissociates, what do you think a weak acid does? Bryce, go ahead, Donatella. So what that means is if you started off with 1 mole of hydrofluoric acid, maybe it'll still be in solution. Maybe you will get 0.1 moles of H plus, 0.1 moles of F minus. So if 0.1 moles of this 1 mole of HF dissociated, what does that mean the other 0.9 moles do? Thoughts? Any thoughts? They stay undissociated. They would stay 0.9 moles of HF intact. The big thing this is HF, does it have a charge on it? Do we see a positive or a negative on the HF? We do not. So this would be considered a weak electrolyte, meaning that strong electrolytes fully dissociate. They fully would light up a light bulb real bright. A weak acid only partially dissociates, okay? So HF, we might want to think is a strong acid. What's another strong acid? Any other guesses? Sulfuric acid is also a strong acid, very good, but only in its first step. H2SO4 is a strong acid in that it makes H plus and HSO4 minus. So if we had 1 mole of this, we'd have 1 mole of this and another 1 mole of this. Sydney on the chat typed in hydrobromic acid. Hydrobromic acid is also a strong acid, okay? There's only about 5 or 6 strong acids that I'm going to teach you. And if it's not one of those 5 or 6, it is thereby a weak acid. Okay. Let's finish the last of these strong acids. What else? Stomach acid is hydrochloric acid. So the acid in our stomachs is HCl. Okay. So HCl, HBr. So we have Cl, Br. What's another halogen? Nobody has their periodic table? What's the best state to go visit? Huh? California? Depends which part. What's the best state to go visit? If I told anyone now, I'll buy you a ticket to any state in the thing, where would you say? Texas? I know you would, Bryce. Who said that? You? Why Texas? Okay. Well, I like Hawaii a little better, okay? I actually just went to Oklahoma and it costs more than flights to Hawaii. So the price of a flight is not always the best. Was it awesome? I wouldn't say it was awesome. It was cheaper than here, that's for sure, other than purchasing the plane tickets and all that. HI, hydroiodic acid. So these 3 halogens are strong acids. This halogen is a weak acid. That we'll talk about that a little bit later. H2SO4, there's 2 other strong acids I want you to know. Nitric acid, HNO3, and perchloric acid, HClO4. So we have a total of 1, 2, 3, 4, 5, 6 strong acids. What do you think the K value of this would be? Large or small? What do you think, Grace? If it's a strong acid and this HCl makes 100% of the products and 0% stays intact, what do you think the K value would be? Large or small? Yasmin, what do you think? What does a large K value mean? Did we just take a test on this? What does a large K value mean, Angelina? It makes a lot of products. So if all of the reactants go to products, what is the definition of a strong acid? A strong acid fully dissociates and it has very large K values. Okay. So did everybody write down these 6 strong acids? If I ask you acetic acid, strong or weak acid, what would you say, Justice? If I ask you, is acetic acid strong or weak, what would you say? Is acetic acid one of these 6 strong acids that I circled? Yes or no? Yes or no? Did any of these be called acetic acid? So what does that mean? That means it's weak. If I tell you phosphoric acid, strong or weak, what do you say, Bronson? Why? Because it's not as strong. So you don't have to memorize every weak acid in the world. You just memorize the 6 strong acids and you know everything else is weak. Does that make sense? So a strong acid, they say practically all the acid molecules ionize, but basically that's what it is. A strong base is a strong electrolyte. This means all of the base molecules dissociate into the ions also. A weak acid is a weak electrolyte. Only a small percentage of the molecules ionize. A weak base is a weak electrolyte. Only a small percentage of the base molecules ionize to form the OH minus and whatever else they're doing. So make sure you understand the difference between a strong acid and base versus you. So sometimes I'll ask you, what's a stronger acid? Okay. If we have a weightlifting contest at Sonoma State and who'd win it in this class? Riley? Someone would win it. Let's say we had a weightlifting contest in this class. Whoever wins that contest, are they the strongest person in the world? But can they be the strongest in the class? So when we say a strong acid or a strong base, we're only talking about those acids and bases. Later on, we're going to look at 10 different weak acids, but can one of those acids be stronger? So of like, HA, HB, HC, HD, I'm just putting random things, right? If I have these 5 acids and they're all weak acids, but one of them is stronger than the rest, could I ask you what's the strongest of these 5 weak acids? So understand the difference between stronger and like a strong acid base, okay? When I say strong acid or base, it completely dissociates. When we're talking about weak acids, could someone be stronger than the other weak people? Yes, you can, right? That's a pretty good thing, right? If you're the best here at Sonoma State, are you the best college student in the world? Possible. You don't know that, right? But in general, you always have to look at what you're comparing things to. So I want us to be aware of that. So since strong acids fully dissociate, we write that with a single-sided arrow saying that HCl, when it reacts with water, makes H3O plus and Cl minus. Remember we said that H3O plus is the same as H plus. And since H2O is a liquid, we sometimes leave out, or we do leave out liquids in equilibrium constants. So just so you know, if you felt like the chapter 14 on equilibrium was confusing, don't worry. The next 2 chapters are all equilibrium, just specific equilibrium looking at stuff. So this chapter that we're talking about is going to be the equilibrium of acids and bases. So what was the equilibrium letter? Donovan, what letter represents the equilibrium constant? Nope. It was a single letter, K. K was in both chapters, right? There was the rate constant, little k. There was the equilibrium constant, capital K. So when we're looking at acids, we're going to look at the equilibrium constant of an acid. We're going to call it a Ka, okay? This is going to be the equilibrium constant of an acid. What do you think the equilibrium constant for a base is going to be called? Kb. Very good. So we're going to have equilibrium constant for acids, equilibrium constant for bases. If we were to write out the equilibrium constant for this, what is the equilibrium constant for hydrochloric acid? Tell me what it should be. Ida, Ka for this acid is what? What goes on top? Okay, so what's the products? Good. Over. Why don't we put the H2O in there? Very good. So if something like a strong acid has a very large Ka value, like Yasmin said, that means that this concentration is really high, that H plus and the Cl minus, and again, I write H3O plus as H plus. These are interchangeable, over the amount that is over here. Now, technically, if we say it 100% dissociates, that would mean that this value is 0. You can't have 0 on the bottom, right? So it's not complete dissociation. Maybe one HCl stays intact, but in general, you're getting everything separated, okay? So the strong acid table, write this down, take a picture. No notes on this next exam because no one talks in class, okay? If people start talking in class, then I will reallow. But if I ask a question and I have to call on someone, so if I have to do that 3 times a day, then there will be no notes on the next exam. What's up, Jack? It is not in order of strength, okay? These are in order of these 3 are all at H's with halogens, but notice that HF is not on this list, okay? The reason why F minus is not on the list, what is the property of fluorine? It's super electronegative. I don't know if you remember that from 115A, but it likes to grab protons, so it likes to be intact as HF. So HF is not one of these. Nitric, perchloric, this one's not that common. I'll probably never use it. This one is a diprotic acid. What do you think diprotic means? Huh? 2 protons. Oh, look at that. It has 2 protons. Weird how so many things in chemistry make sense based on the name. Okay. So should you memorize this list? Yes, because as of now, you can't write it on a list, but you should still make a list just in case I soften my stance. Weak acids only donate a small amount. So we say HF is a weak acid. It has a double-sided arrow. Much less than 1% is ionized in water. We can actually calculate the exact amount of a weak acid that ionizes. Anybody have any ideas how we're going to do that? Take a guess. Take a guess. What's something you've learned in equilibrium that helps you solve for concentrations? Good guess, but not correct. Think about something that you might do. Very good. Ice tables. So we can make an ice table, and if we know the Ka value, we can calculate the exact concentration of H plus and F minus that's in solution. Are we going to do that in great detail for the next 2 to 3 weeks? Yes. Are you ever going to do it in your life? I doubt it. But that's the curriculum that I'm set to teach. I'm sorry about that. Okay. Some examples of weak acids. All of these are weak acids, and every other acid that's not a strong acid, okay? But these are some common weak acids. Hydrofluoric is the one we're going to use a lot. Acetic acid is one that we see a lot. Where's acetic acid found? Huh? Vinegar. Vinegar is acetic acid. Where is carbonic acid found? Soda and stuff like that. It is carbon dioxide dissolved in water. Yes. Sulfurous acid looks very similar to sulfuric acid. The only difference is this is SO3. The other one was SO4, so don't get those confused. Phosphoric acid is very important in our bodies and things like that. We have phosphates, DNA, and stuff like that. Look at this list of strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide. If we were to look up a periodic table, notice that lithium, sodium, and potassium are all in the same row, right? Strontium, calcium, and barium are also Strontium, barium, calcium. So the alkali metals and the alkaline earth metals, when they are combined with a hydroxide, are all strong bases, okay? You're not going to have to memorize these as much. But what we will see is, so as you can see, most strong bases are group 1A and 2A. The group 1A metal hydroxides are highly soluble in water and can form concentrated base solutions. The group 2A hydroxides, however, are only slightly soluble. So that's why we use those in things like antacids. You don't want to just drink a big old bunch of sodium hydroxide, because then it will not only neutralize all the acid in your esophagus, but it will also like tear up your stomach. If you were to take like a pill that has calcium hydroxide or barium hydroxide, it will only become in solution enough to neutralize the acid that it needs to react with, and then it will just stay as a solid and you'll pass it through your body. So that's why those are nice, okay? We'll get into bases later, but generally if a base is not on the strong list, it's usually a weak base. So let's look at the equilibriums from these. A strong acid has weak attraction with its conjugate base. So if HA is the acid, A minus, what's the name for it? That's the conjugate base. That is the acid after it gives off its proton, okay? So a strong acid has these things do not want to stick together. That's kind of the definition of a strong acid. The conjugate base is the weakest base. It has no desire to grab a proton. A weak acid, like HF, as I said, F minus likes to grab that proton. It is attracted to it, so it stays stuck together in solution. So that's the main difference between a strong acid and a weak acid. Strong acids completely separate. Weak acids separate a little, but they stick together a lot. The reason why they're not strong electrolytes is because when they're stuck together as HF or Hc2H3O2, they have no charge. Therefore, they are a weak acid. The stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. Skip that. Skip that too. That's not going to be important. Acid strength is measured by the size of the equilibrium constant. So as I just said earlier, we have this. We can get rid of the water. So remember, H3O plus and H plus are the same. So if we say this reaction is what's happening, it's happening in water. It's really H3O plus, but it doesn't make a difference. So what we say is the equilibrium constant for an acid is equal to H plus times A minus over HA. Everybody feel comfortable with that? That's just taking the law of mass action and writing that over there, okay? So like I said, we're going to eventually make ice tables for these things. We're going to have to solve for the concentrations of all these things. You're going to do this in lab also. I think so we don't have lab this week. Starting next week in lab, I think we're going to do some experiments where we have to like find some acid. In general, the larger the Ka value, the stronger the acids. Therefore, if we look at this list, this has Ka values of 1 times 10 to the negative 2 all the way down to 1 times 10 to the negative 10. Which is the strongest acid on this list? What do we think? Huh? Yeah, Bronson.
Top one,
Why?
the largest K value.
Strongest acid. 1.1 times 10 to the negative 2. That doesn't seem like a big number, though. Isn't that
Biggest one that's
0.011? So once again, it goes back to, of this list of acids, it is not that strong of an acid, but when you compare it to this value down here, which is 0.00000000013, and I probably didn't even draw enough, this one would be the weakest acid of the group, okay? So the largest Ka, so this is the strongest acid on this list. This has the smallest Ka, so it has the weakest acid on this list. Everybody comfortable with that? So if I'm asking you to rank, formic acid hypochlorous acid and nitrous acid, which is going to be the strongest of these three? The highest on the list, because this list is ordered from Ka values, highest Ka to the upper right to lowest Ka to the bottom right over here. So this would be so if we were going, number one is strongest acid, number three is weakest acid, we would go 1, 2, 3 in that order over there. Everyone comfortable with that? Trust me, it's not going to be that easy. So consider the following two acids and their Ka values. Which acid is stronger? Shout it. Why? Higher HF is, since it has a larger Ka value. Should we just make the whole test based on which is the strongest acid? That'd be nice, right? But then you'd really learn nothing. And why are you in college? To just come in here and get a good grade? No, you want to learn some stuff. So, will you ever use this again? I will leave that answer unanswered. Maybe you're going to be a acid engineer or something like that. Which conjugate base, F minus or Cl minus, is stronger? So this one takes a little bit of thinking, Bronson. So you think that weaker acid has a stronger conjugate base?
Yes.
Everyone agree with that? That the one that wants to grab the protons more is going to mean it's going to want to release the proton less, right? So a weaker acid is less willing to let go of it. That means it is, in fact, the stronger base in those situations, right? Okay. So water. Anybody know the formula for water? H2O. So water is an amphoteric substance. Have you ever heard the term amph before? AMPH. Where have you heard the word amph before? And what is an amphibian? It's something that can survive in water and land. So in this case, water is an amphoteric substance because it can act as either an acid or a base. So if I ask you to show water acting as an acid, what would you write? Water plus a base, let's just make a generic base, makes BH plus OH minus. So this water becomes OH minus. It lost a proton. The base gained the proton, right? So in this case, water's acting as an acid. That same water molecule can react with an acid. So let's just say HA is a generic acid. So if HA reacts with H2O, it can become H3O plus A minus. So the HA loses a proton. The HA is the acid. The water gains a proton, therefore is acting as a base in this case. So water is amazing because it can act as a base, as we do when we react it with an acid, or it can act as an acid when it reacts with a base. So everybody see that? Water is amazing because it can react with both. About 2 out of every billion water molecules form ions through a process called autoionization. So at any given time, if I have a cup full of pure water, if there was 1 billion water molecules, about 2 of them, or one of them is a H3O plus, one of them is a HOH minus. Okay. All aqueous solutions contain a little bit of H3O plus and a little bit of OH minus. So what happens is the concentration of H3O plus and OH minus are equal. Using this ratio, the concentration of H3O plus in pure water is equal to the concentration of OH minus, which is equal to this value of 10 to the negative 7th molar. Okay. Where does that number come from? Somebody did some math. Okay. Let's just believe it. Okay. What comes out of this? The product of the H3O plus and OH minus concentration is always going to be the same number based on equilibrium. So what this tells us is the ion product of water has a symbol of Kw, also known as the dissociation constant of water. And the H3O, the H plus times the OH minus in any solution will always equal Kw, which is equal to 1 times 10 to the negative 14. Because remember we said 1 times 10 to the negative 7 times 1 times 10 to the negative 7. That equals 1 times 10 to the negative 14. So what that means is if we add acid to this concentration is going to go up. What's going to happen to the OH minus concentration? Since this is an equilibrium value, this number is constant. When we add acid to a solution, that number times the concentration of OH minus, this thing is going to have to go down to make it equal to this number, right? Just like Le Chatelier's principle, kind of. So they're inversely proportional. Why is this important? Why it's important is we are going to get a formula out of this. The Kw, so these formulas are important. Kw, which is 1 times 10 to the negative 14th, is equal to the H plus concentration times the OH minus concentration. So if I give you one of these, can you solve for the other?
Yeah.
Yes, we can, right? So let's say we have, so in this case, it says, suppose OH minus is 1 times 10 to the negative second. What is the H3O plus concentration in that solution? Everybody pull out your calculators and try and do this. If math wasn't heavy on the last test, math is super heavy on this next test, okay? So you're going to take this value, right? We're going to plug 1 times 10 to the negative second in over here. So basically, the H plus concentration is going to be equal to 1 times 10 to the negative 14th divided by 1 times 10 to the negative 2. So someone punch that into your calculator. Tell me what you get. 1 times 10 to the negative 12. When we rearrange everything, we should be getting 1 times 10 to the negative 12 molar. Everybody see how we do this? In basic solution, so when a solution is neutral, H plus is equal to 1 times 10 to the negative 7th. OH minus is equal to 1 times 10 to the negative 7th. This is what we call a neutral solution. Equal amount of OH minus and H plus. In this solution, we have 1 times 10 to the negative second molar H plus and 1 times 10 to the negative 12th molar OH minus. What are we going to say? Actually, this is backwards. This is the OH minus, sorry. That's OH minus. This was H plus because they told us OH minus was 1 times 10 to the negative 2. So what is there more of, OH minus or H plus in this situation? The OH minus has a larger value, so OH minus is greater than H3O plus. We say that this is a basic solution. Have we ever dealt with basic solutions before? Or acidic solutions? So that's something that we're going to look at now. You should be able to calculate all of these just by plugging it into the equation. For part A, we're going to plug 7.5 times 10 to the negative 5th into H3O plus, solve for OH. Or actually in this one, this is just saying determine if the solution is acidic, basic, or neutral. Do you think we can do this without calculating? How can we do it without calculating? Bronson?
Multiply values with exponents, you just add it together. So whichever exponent's bigger.
Okay, but is there like a middle range when they're equal?
7.
So when you have something equal to 1 times 10 to the negative 7, that means that OH minus is also equal to 1 times 10 to the negative 7. If we get that value in our head, now when we look at this first problem, the H3O plus is 7.5 times 10 to the negative 5th. Is that bigger or smaller than 1 times 10 to the negative 7? It's actually bigger, right? Negative 5th. Would you rather owe me $5 or $7? 5, right? So sometimes a bigger number is a smaller number when it's negative, right? So if you just look at the number, this one is that is greater than the 1 times 10 to the negative 7, which is our benchmark for neutrality. So H3O plus is greater, the solution is acidic. Is this number bigger or smaller than 1 times 10 to the negative 7th? Smaller. That means that that solution should be basic. You can actually quantify these. Bronson said something about, so you can figure out these numbers here, 10 to the negative 10th times 10 to the negative 5th. Sometimes when the numbers aren't 1, they don't just do it exactly. But you could still just see, if it's not times 10 to the negative 7, you just think of if it's bigger or smaller. If you have to calculate it, you have to do it. When it is times 10 to the negative 7, that means that they both are the same, and that is a neutral solution. Okay? So a neutral solution contains equal amounts of acid and base. An acidic solution contains more acid. A basic solution contains more base. This formula, Kw equals this number, which is equal to these two things, helps us solve for any of those concentrations when we're doing this stuff. Okay? So bring your calculators on Friday so we can start doing this. All aqueous solutions always contain both of these things. Neutral solutions have equal amounts. Acidic is greater than 10 to the negative 7th, and the base is going to be less. And base is going to be greater than 1 times 10 to the negative 7th, and acid is less. So that's summarizing. These numbers suck, right? Do we like seeing numbers like 7 times 10 to the negative 3, 6 times 10 to the negative 8? I don't like dealing with numbers like that. So in science, we don't want to talk about acidic and basic concentrations in these exponential numbers. So what we do is we convert them into pHs, okay? The acidity or basicity of a solution is often expressed as a pH. Who can tell me the different pH ranges for acids and bases? Anybody know? So pH equal to 7 is what we call a neutral pH, meaning that the concentration of OH minus is equal to the concentration of H plus. If the pH is less than 7, then that means it is an acidic solution. Notice that all these numbers that are less than 7 are red. Gastric juice, human stomach, limes, lemons, peaches, vinegar on here? Nope. So pH is less than 7 is an acidic solution. That means that H plus concentration is greater than the OH minus concentration. And that means it has to be greater than that 1 times 10 to the negative 7. When it's a basic solution, the pH is greater than 7. And the pH scale, they say, runs from 1 to 14, but really you can have negative pHs, you can have pHs higher. I'll show you how to calculate that in a second. So the way you solve for the pH is P of H. Whenever you see this P, that means negative log of something. You're going to type that into your calculator. And for the capital H, you're going to type the negative log of whatever the H3O plus concentration is. So if something has a H plus concentration of 1 times 10 to the negative 4 molar, what is the pH of this solution? Somebody go ahead and calculate that for me. You're going to do the negative log of 1 times 10 to the negative 4. Type this into your calculator, see if you get the answer that we all get. If you don't, maybe you're not using your parentheses and stuff right. What'd you get, Sophia? Anybody get it? We got a pH equal to 4. Is this value larger than 1 times 10 to the negative 7th? Yes, it is. Remember, 1 times 10 to the negative 7th is neutral. 1 times 10 to the negative 4 is a larger value. Should the H plus be an acidic solution? Remember, we said less than 7. That is acidic. We feel confident about that. Okay. For basic solutions, the OH minus concentration is bigger. If you want to find the pH of a basic solution, if I tell you the OH minus concentration is 1 times 10 to the negative 2, and I think we did this one, right? Remember we did this problem? You can't directly calculate the pH from this, but you can do, okay, with the OH minus concentration, I can find the H plus concentration. Remember, we did this over here when we had 1 times 10 to the negative 2 for OH minus. That said that the H plus was 1 times 10 to the negative 12. So 1 times 10 to the negative 12. This gives us a pH equal to 12. Okay. So when you do a log of stuff, it's kind of backwards, right? Because you're taking bigger numbers and making them smaller and smaller numbers and making them bigger. So you can calculate this stuff. That's the end of class. We will continue this on Friday. Aloha. If anyone didn't take the test, you better do it by tomorrow.